Hi and hello everyone. What we have seen so far are all queuing systems or queuing models which are used to model a single node or a single service facility kind of thing, right. So, all these things then we can together we can call them as single node queuing systems. Okay. But in reality, there is very less likely that you always encounter only a single node service system. Okay. As opposed to this, you have what we call as network of queues or queuing networks, where more than one nodes are connected in some sense, and the service has to be obtained from more than one node. So, that is the topic of our further analysis in the next few lectures. So, what we are going to study are these queuing networks. In general, it is called all networks of queues, okay. And this is an important area and which has wide applications in diverse fields which occur quite naturally. And because of the complexity of this also pose extremely difficult problems for the analysis also, once you go little bit beyond that. Okay. So, that is the nature of queuing network. Okay. So, what we have, while a single node, okay, while a single node queues represent situations where the customer demands one service, right, that is what we say. Meaning that suppose if you go to a petty shop kind of place where you just go and buy something and come, that is it. So, that is a single node system basically maybe. But whereas if you go to some other place, right, even when you want to get service, say in an airport terminal for example, first you have to this luggage screening, then checking in, then security check, then like you have multiple stages where you need to go through, and that is a situation that will come here actually, right. So, a queuing network on the other hand represents situations where a customer may need more than one service or different kinds of service. If you are going to a hospital for example, where first you may be seen some preliminary investigation, then some test followed by some specialist examination and so on, right. Different kinds of service might be there. Okay. So, this may be from different servers and may be required to wait before each of these different service channels for service. Okay. Bank counters, going from one counter to the car repair facility, for example, when a car is being repaired, it is not that every part of the car needs repair, right. So, there may be one service facility, right, or service repairman or so, like who will repair only the batteries, someone will look after the tires, someone will look after the engine component, right. Like this different people will be there. A car may not require repair from all the service, but it has come for repair. Right? So, you will have a scenario where they will go through some of the nodes, right, some of these service centers for a complete service. The whole system is now a network, right, and the customer would need to get service from more than one nodes possibly. Even if it is one node out of those network nodes, it is fine, but some customers will need in 2, some customers will need in 3, that 3 could be different for different customers and so on, right. This is a scenario that you have here, and that is what is trying to model through a network of queues. Here, why we have to do it as a network rather than as a single node? The reason is clear, because only after you do one processing, right, hospital for example, if you take it, only the preliminary investigation or the screening is done, then doctor will prescribe what are the tests to be done, then accordingly you go for the other tests, and then specialist will come, then some more tests, some more screenings and so on, things will go. So, it has to go through. So, from here first stage you will go to the second stage, you directly will not go to the second stage, right. Suppose if you call this as first and second stages, So that kind of scenarios it will come. So it has to be networked. It is not like individually you can study this. So when you are studying together, obviously the problems will become more complex, and that is what we are going to encounter. But it has diverse application, and it's quite naturally occurring in different situations, like assembly lines where products are being assembled part by part in each stage, right. Maintenance operations, again the car repair facility, we thought maintenance of also in a similar way. Airport terminals, quite naturally in computer and communication systems and networks. So you have communication networks, computer network, that's how you call it by nature, because things are networked together and it has to pass through different stages, right. Even if you are some multi-programming system that you have in mind, or a cellular network kind of thing that you have in mind, anything like it has to go through multiple nodes, what we call in general, right. So what we give here is certain basic concepts and we results in a very simplified setup. That's what we are going to consider, but they are also useful in their own light, and then they do throw enough light on the behavior of the such queuing networks. In general, what you can expect, and in general what you have to look for in such queuing networks. It will exhibit these ideas here, and again this itself is an important in many designing of many manufacturing or production facilities or computer communication networks and so. Of course, we may not go to a deep except at the top layer level. So there are many good books that available if you want to get a deeper understanding of this. For example, both Gillenby and Puzol, like and host of other, like there is Kelly's book is freely available, which is a very classical one, and then Walrand and so many other books are there, right. Fine, of course you can find, and then they can be looked into for a detailed look into this topic. So basically what we have is you are looking at the study of queuing networks. Now what are the different types of queuing networks that one can broadly classify into them? Okay, we basically have three. Of course the third one is a mixture of the first two, so you can call it, even you may say it open and closed alone, that maybe you can classify them. So what do we call by when we say open queuing network? So here what situation is there? Customers of one or more classes enter the system from outside, may not be from the same node, or it may be from different nodes they may enter, and they pass through different stages or different nodes in their own as per the requirement, as per the design, and eventually they will leave the system after service at one or more nodes. So there is an input to this system, which is what coming from outside, external arrivals are there, and after getting service in one or more nodes, they eventually leave the system, right. So that's the kind of thing what we call open queuing network. As opposed to this open queuing network, we have what we call closed queuing network, where what happens is that a fixed number of customers, again they could be of single class or multiple classes, circulate in the system, moving from one queue to the next and getting served at individual nodes. Okay, so here no external arrivals happens and no departure happens from the system. It is just that there is a fixed number of customers, right, who move from one queue to the other and get their service done, right. So that is what is closed queuing network, and as the name suggests, mixed queuing network is basically consisting of both these, open and closed, right. So it is open for one class of customers and it is closed for another class of customers, say. So it is not just for one, it could be for some number of, suppose if you have multiple classes of customers. So there is at least one class for which this is open, there is at least one class for which this is closed. Whereas in open and closed, all of the classes, if you have multiple classes of customers, so all of them have to be either a single type, either open or closed, to be called as open or closed queuing network. So we might mainly concentrating on this open and closed network only. Now let us see how does an open network would look like. Okay. Say for example, there is an arrival, external arrival happens, right, which comes to our node basically, right. Suppose if this could be one or more server. So, I am just putting a single. So, there could be one or more servers could be there, and after getting served, right. So, they may go here, another queue, okay. Again there are one or more servers, this is one way, or they may come here, again there are one or more server, right. And after doing this, what could have happened? So, here it might so happen that from here, right, when some may go out, okay, for example. So, they are going out, some of them, right, again it comes and join in this queue, right, possible. And from here again, it either some goes out or come and join in this particular queue, for example, right. It could be very simple 3 node. For example, you can think about this being some product has come for some repair, and depending upon after certain processing it has been sent to here, and after being repaired here it is being sent out, or after noticing that there is a further defect into this which need to be rectified by this repairman, it may be sent here. Or in this case it can come here, for example, in this line, so it is recognized here and then it is sent here. Now, after doing service, like it may go out as a good product, or it may send back to this for some more processing because there is something issue here, right. So, this is something. So, here what happens here is that there is an external arrival. So, it could so happen even in this particular case. So, there is this kind of arrival also can happen to this system, right. So, in this situation, what you are seeing is there are 2 places, right, the arrivals happens, arrivals here and arrivals here. There are 2 nodes in which departures happens this, okay. In these 2 nodes there is departure happens, in these 2 nodes again arrival happens, right. So, it could be need not be from the same entry point. So, that could be from in this there is no arrival, it is possible. But similarly, in this there is no external departures. Of course, after you may have a situation where from this also a departure can happen. So, that is a more generic versions that you have. So, this is what we call it as a open network. Okay. Now, as opposed to this, now what will happen in closed queuing network? Okay. So, you have some number of servers here, and then this goes here. Again it is done by some number of servers, and here from here it can go here with some number of servers here, and from here, right, from here again it can come here, and from here again it can come here, right. So, this is one simple scenario, or from here it can also come here, right, for example. So, this is what we call it as the closed queuing network type, right. So, this is a typical example of a closed queuing network, okay. So, here what you see here in this scenario is that there will be customers here in this for waiting for service. There could be one or more servers here, that is what we are depicting it here, and you see here there is no external arrival to this system, the whole system, and there is no departure either from this particular system, right. So, this is what is called closed queuing network, this is open queuing network. If there is at least one node in which to which the external arrivals happens, and if there is at least one node from which the customers depart. See here customers and server, jobs and service, whatever is the case, processors, processing, and these are commonly used. So, do not worry about that, okay. That is as usual with all those things that you have here in this terminologies. In queuing network, even if you look at certain books, like they will use such words more commonly, but it is one and the same as we said repeatedly, customers, servers, we will use that. So, this is a closed. Now, So, here this kind of things that you have here, right, this is depends on what happens, like for different classes how it treats and so on, one can have more complexity being involved into this, but this is a basic structure here, right. What is an open and closed simply means that it can come from outside, go out of the system is what open queuing networks. Closed queuing networks are the one where a fixed number of customers circulating in the system, moving from one queue to the next, and then so in each of these, so for example when you go here, there are many issues that can crop up, we will see one by one, okay. So that is what we will see. So just as in the case of single queues, performance measures of a queuing network can also be obtained, and of course we need it, so it can be obtained also. And one important measure is the time taken to serve one customer in the system. So this is more meaningful here because in the open context, because someone coming from outside and then eventually he leaves the system, right. So it may so happen that this particular customer may loop n numbers so many times, and it can go and again it can come, he can loop many times before eventually he leaves the system, right. So in that case, the time taken for serving one particular customer in the system is what is more relevant here, okay. The analysis would give us measures for the number of customers in each node, so that estimates of buffer requirements can be made, right, because this is what we call it a single node, right, single node queuing system, and so far whatever we have been studying are all studying about this particular part, okay. We are not bothered about whether the arrivals to this system happen from here or happen from here and so on. Together we assume that there is a arrival process which is captured by the assumption of say a Poisson process arrival model, so far whatever we have considered and so on, right. So this is what we have studied. Now they are all interconnected in this way, right. So that is what makes this as study is complex, but again much like the single node, what your main interest was the number in the system, in that particular queuing system. So even in network also, what we generally look at is that number in the system in each of these nodes. What is the number in the system here and here and here is what we are together we are looking at it, okay. So that's, so if each node is what, then we look at it, the number of customers in each node, it helps us in two ways. One is that we can estimate what should be the buffer here we need to keep, okay. And also when you look at this in that way, rather than see, one way is the whole thing can be thought about as a queuing system without regarding this individual queues inside. So you can assume that there is an arrival to this system and finally they are departing, right. So no matter how internal process is there, then you can think of it as if, but that is not really the case, and that does not give you a correct picture of what is going on inside. A patient coming to a hospital, from his arrival to the hospital till he leaves the hospital, you can treat it as if the whole thing is the time he spends in the hospital as in a single node. But to get a finer understanding, you need to model individually, so that the bottlenecks, right, the reason for that is that the bottlenecks can be identified, whether they are queuing it up more in the registration counter or the first level doctor service or in some technician's lab, right, or they are queuing up for a lot of time in the specialist place. Which one is where, what exactly is happening? If you want this finer picture of it, then what you need to know is that you have to treat this individually as nodes. Each one of them is a queuing node, and then you look at their number in each place. So that the bottlenecks may be identified, right, and that will lead to obviously to the better design, so that you can decide then. So suppose if in a specialist place is lot of queue is there, so what you can do, either you can think about increasing the specialist, or at least the waiting space you can make it larger in this case, right. So that's a better designing aspect, right. So to do that you need to understand. That is why we say that it is easier to model a complicated service scenario as a queuing network in order to capture better the way the service is actually provided, rather than treating the whole thing as a single black box, right. Rather than that, if you do it individually, that would play a much more convenient way you can capture the behavior. And just like the single node queuing systems require some specifications vis-a-vis, like if you want to specify or characterize that particular system, the network of queues also requires some additional specifications, as you would have by now observed. The first thing is interconnection between the queues. Okay. What is that? Suppose if I look at here, how this particular node is connected to this particular node and this particular node and so on in any queuing network. Say for example, from here, right. So, this from this node is connected to this node and this node, fine. This node is connected to this node only. It is not connected to this particular, the node 1. Suppose if I call it, if I want to give the name, this as say node 1, node 2, node 3, suppose if you want to call that way. So, node 1 is connected to node 2 and node 3, node 2 is connected to node 3, node 3 is connected to node 1, right. In which way, right. If you have more number, then you know really how things will. So, after the customer is finished service in node 1, what are all the place where it's possible for him to go, that may be depending upon the requirement, right. So, what are the possible ways? So, that is what is the interconnection. So, the interconnection between the nodes need to be specified, right. So, where he will go. For example, from node 3 he cannot go to node 2, he can go to node 1, that has to be specified, then only the connection is complete, right. So, the interconnection is an important component here, and that really makes this as a network, and from one node, after he finished service in one particular node, what is the next node for the customer, right. So, that has to be specified by the interconnection, that is important. The second is the routing strategy, which could be deterministic. For example, in this particular case, for example, if you see in this closed case, so from here there is only one way he can go to, we will come back to here, right. But from here he can go to either of this, from here it can go to this or this, but this is one place where you see the deterministic way of moving, okay. So, from this customer, after completing service, he need to be routed to either this or this. So, what is the strategy that you are going to adopt, right? It could be deterministic, one way, right, or it could be class based. So, you could have scenario, say for example, even in this particular case, like we are depicted as arrival happens here, but really the arrival could consist of two classes, okay. The first class, after completing service here, will move to node 2, and the second class, after completing service here, will move to node 3. You may it may be of that nature, right. It is possible in that way, and after completing this node 3, the second class, right, suppose if it is not there, if it comes back to node 1, then basically this becomes a mixer kind of thing. When you have classes, two classes acting two different ways, it depends on specification. It's the same network, with can be in that manner also, or it could be probabilistic, completely probabilistic, with what we call it as routing probabilities, right. So, from here, so for example, I can specify a probability p here and this is 1 minus p here. So, after completing the service here, in a completely probabilistic manner, the customer may move to node 2 with probability p and may move to node 3 with probability 1 minus p. Then these probabilities, this p and 1 minus p, is what is called as routing probabilities, okay. So, the routing probabilities, if it is probabilistic way of routing, so then it has to be specified that what is the nature of this probability. These probabilities have to be specified. So, this defines the routing strategies. Okay. So, it could be either deterministic or it could be class based or it could be probabilistic. In either way, in all these way, which is the strategy that is being followed, you need to specify under the routing strategies. Okay. So, that is interconnection first aspect, and how it is being customer is moving from one to the other queue is what will be given by the routing strategies. And then you have the strategy to handle blocking if the destination queue is a finite capacity. Typically what we might hear, so here we might assume that all these nodes are infinite capacity nodes, meaning any number of customers can queue in front of this server, right. Everywhere we can assume that way. But on the other hand, it is not really the case in reality, and if you want to bring that fact into this, now if you assume that this node 2 is finite capacity, assume for the time being that node 2 is of finite capacity, then suppose either from the outside when there is an arrival happens when the node 2 is full to its capacity, then you have seen earlier itself, like this is something like a blocked arrival here, what happens, right. So, you can decide what to do with that. You can simply it is lost or it is blocked calls cleared system or what, it has to be there. But if it comes from other, again if it comes from the other node, for example, after completing the service in this particular node, he has to move to this node 2, but node 2 being a finite capacity one is already full. Now, what is this customer is going to do, right? Whether he will keep on holding to this current server, because he cannot leave this, because where he will move. Okay. So, what is the strategy that you are going to adopt, right? So, whether there is some kind of a temporary queue that you have kept for these people to wait there before they are moved to here, right. So, depending upon what you do, and there are many different ways this can be handled. Okay. So, what is the strategy that you are for a blocked customer? Blocking situation can happen if the subsequent queue to which the already served customer in a particular node has to move, if he cannot move due to the blocking that is happening in that particular node because it is already full, then what is happening to this customer, right? Whether he is lost, one way you can think, or he can kept in some temporary buffer, a temporary queue waiting space before a waiting space is created here and he is moved there, another way. There are so many ways one can handle in this way. So, whether you treat the customer who is coming from another node differently from a customer who is coming from outside, everything can be model, and depending upon the requirement, the specifications can be given as to how you are going to treat in that particular state. If he is occupying this and he cannot leave this, and if your decision is this way, that he has finished service here, but he has to move here, but he cannot move because this is full, then he will hold on to the server here. He is not getting service, but he is not releasing the server either, right. So, the server is free, but he cannot serve the next customer. So, you have some issue here also because of this blocking which the customer cannot depart from this particular node. So, this has to be kept in mind when one looks at that. Okay. So, that is the strategy to handle blocking is also need to be specified. So, these are certain additional requirements. Again, these are not all, there could be many more varieties depending upon suppose if you have different classes, then you could think of it as a different way. Different classes, for example, you could think this as rather than single class arrival, multiple classes and so on. One class will go inside the loop, the other class will come and go out of the system, anything like, and also like there may be other specifications that may come. Just like in a queuing system, we have certain basic characteristics to specify. In networks also, these are certain basic specifications that we need to give in order to specify the network completely. Now, in this particular case, it is possible that a customer returns to a queue for another service. It is feedback, right? We said that a customer who is coming here, he will get served here, he will move here, then again he will come here, he will come here. So, there is a feedback here. Okay. So, these are called feedback networks when such thing happens. As opposed to this, you also have feed forward networks. These are open networks with no feedback. Okay. So, in this case a queue will be visited at most once. Some of the nodes a particular customer may not visit, but some nodes at least he will visit, but he will not going to visit that same particular node which he has already visited once, he is not going to visit again. Such networks are all called feed forward networks. Why this we are putting it as feed forward network feedback? Because these features play a critical role or make the complexity of the analysis easier or tougher depending upon whether there is a feed forward or feedback is there in this case. Okay. As we go along, you will understand why. That is why we want to there are many other things like fourth join queue and things like that, which will will come later if there is a possibility of time. So, that kind of things can happen. So, that is why we want to specify certain terminologies, words to make you familiar that these kind of situations, things might be easier or little tougher depending upon what the features that you may have. So, since in a network, since this kind of thing can happen, right, a customer may visit all 3 nodes and again he may come back to node 1, right. He can go here, come here and then go again come here, possible. So, it is possible in this particular scenario, but still he can come back to this, right. So, the feedback is a very much a possibility in general in such networks. So, if you do not have feedback, then feedback essentially in production and everything could be represented by the defective items cases, right. So, that is possible, one has to keep that in mind. Okay. So, these are certain basic notions, basic ideas about queues. Now, let us take a very simple 2-node queuing networks and see what we are trying to do is that the number of customers in each node, we will see like what happens to that. Okay. So, we consider the following very simple network of 2 queues or 2-node queuing network in a way, where what happens, there are 2 nodes, right, there are 2 nodes or 2 queues which are interconnected in this way. Right. Customers arrive to the first node according to a Poisson process with rate lambda. Okay. So, this queue, so to node 1, suppose if I want to call this as node 1 and this as node 2 or first node and second node. Okay. So, for the first node, the customers arrive according to a Poisson process with rate lambda. This is a single server system and the service time here is exponentially distributed with parameter say mu1, and this has an infinite queuing capacity and the service discipline here FCFS. So, this first one is typically is an MM1 queue is what we are saying, right. Now, after completing the service in first node, once the service is completed in the first node, the customer moves to second node, okay, which is also a single server system and with exponentially distributed service time with parameter mu2, and again the queuing capacity here is infinite. So, this is also an infinite capacity and again the queuing discipline is FCFS, right. And after completing the service at the second node, the customer will leave the system. Okay. So, no feedback happens either after first stage or after the second stage, or no departure happens after the first stage, or no arrival happens at the second stage. Okay. So, the second stage could be represented in this manner, like there is some arrival process, right, but the service is exponential M and there is a single server, infinite capacity, FCFS, everything is there. So, this whole system, right, which is basically this is in series, could be represented as MM1, after this the customer moves with this is the arrival process to the, so the output from node 1 act as a input to node 2, right, and again it has this. So, this is the structure, or this is what the description that you can give for this 2-node network. Okay. So, this is what is happening. Now, you see things are all exponential, Markov chain assumptions do hold here. So, if I denote the number in the Q1 or the node 1 as some n1 and this n2 as the number in the system n2. So, the total number in the system can be represented as a 2-dimensional continuous time Markov chain n1 and n2, right, and with state space as small n1 n2, where each n1 and n2 could be 0, 1, 2, 3 and so on. So, there could be 0 customer, 1 customer, any number of customers in any of these nodes. So, that is the state space then. Now, if I denote the corresponding probabilities by P n1 n2, right, this is the probability of n1 customers in the first node, n2 customers in the second node. I mean, we are in the system only we are looking at it, not in the queue alone, right. When we say in the queuing network, in the first queue, second queue, but we always mean the number in the system, that you have to understand, right. Just because the word queue is used does not mean that it is number in the queue. So, it is always number in the system when you are talking about this kind of thing. So, P n1 n2 is the probability that n1 customers in the first node, means first queue or first queuing system, n2 customers in the second node. Then, right, the steady state solution for this exists under the condition, because each one, the first one is mm1, which will be stable only if lambda by mu1 is less than 1, right. So, the second one also rho 2 is lambda by mu2 less than 1, under the condition that this CTMC is positive recurrent and has a steady state unique limiting steady state distribution, and that can be obtained from the balance equations. Now, you look at the balance equation again in a similar way like what we have used to write in so far in all these Markovian models. You have the similar scenario here, right. So, look at the state n1 n2, right. What are the possibilities in which you can reach n1 n2, right. You could have been in n1 minus 1 and n2, and there could be an arrival to the first stage, right, to bring the state to n1 n2 from n1 minus 1 n2 to n1 n2, or there could be n1 plus 1 in the first stage and n2 minus 1 in the second stage, and there is a service completion at stage 1. Then this one customer from stage 1 is moved to the second node, right. So, the second will become n2. So, it will become, after service completion in stage 1 or node 1, n1 plus 1 and n2 minus 1 would move to n1 n2, and or there could be, the system could be in n1 in the first node and n2 plus 1 in the second node, and there is a service completion at node 2 to bring this state to n1 n2, right. Again, this is again similar to this, where it can move either an arrival can make it go out of state n1 n2, or a service completion of phase at stage 1 or a service completion at stage 2 can make the process move out of the state n1 n2, so the left hand side. Now, these are all boundary. At n2 equal to 0, what would happen, right. So, there could be only these two are the two possibilities that can happen, right. So, this is not possible in that case, because n2 is 0. So, there could be, and if any service completion in stage 1 would make n2 is 1, it is not 0. So, that is what would. So, this is what you have. Again, you can take this, and this is the boundary cases n1 0, 0 n2 and 0 0. Okay. Now, so this solution to this is fairly easy to obtain. It is not very complex. In the usual way one can proceed, right, and it can be shown that P n1 n2 is some constant time. So, here constant is appears to be P00, rho 1 to the power n1, rho 2 to the power n2 times P00, one can show. For example, from this first itself, P01 is rho 2 times P00, right. That is what you will get from here, and recursively, like, you can go back and then you can obtain this relationship. And from the normalization condition, if you do, now already we know rho 1, rho 2, both of them are strictly less than 1. So, my P naught naught can be obtained to be 1 minus rho 1 and times 1 minus rho 2. Thus, the complete specification of this P n1 n2 is given by this. Now, if you look at here, this is a geometric distribution with parameter rho 1 and this is a geometric distribution with parameter rho 2, and this is the first one is already it is an MM1 queuing system, and this is nothing but the steady state distribution of number in the system in an MM1 queuing system, and this is also similar thing that you are obtaining, and that is the quantity, or that is the nice things that you are seeing it in this expression here. Now, this tells some stories, right. So, what is this? This is the joint distribution of number in the system, or number in the number of customers in node 1 and node 2 together, and this is, you can think of it as if the number of customers in the system in node 1 and this is number of customers in the node 2, both of them behaving like an MM1 queue if you think. Okay. So, that is what it is. So, a queuing network of this type where the joint distribution of the number of customers in each node can be written as the product of terms involving the number of customers in the individual nodes is what is generally called as product form network. What we mean is not this expression, but we mean this expression. Okay. So, some constant times, this is joint distribution of n1 and n2. So, this is some function of n1 and some function of n2 multiplied by some constant is what is the form that you are having here. And any network where you get this kind of situation, we will see the analysis becomes much simpler in that case. So, that is what is called as product form network. Okay. And in many situations and under some conditions on the parameters, this type of solution is observed to hold either exactly or approximately at least. So, that the whole theory, there is a whole lot of literature on product form network itself, because like in this case things will become much easier. Imagine that this is the case and then you are looking at a function of n1, a function of n2 and a constant, right. Now, if I want to obtain the mean performance measures, right, I know, right, in this particular case that I can handle this very easily because of this product form that you have here. There is nothing like rho 1 to the power n1 plus or n1 n2 kind of terms, which you cannot separate it out, right, whereas n1 plus n2 or rho 1 to the power n1 and rho 2 to the power n2, it is very simple here, or anything that is a function of n1, function of n2 multiplied by a constant is what should be the form, and that is what is called as the product form networks. Okay. So, this is a example of a product form network, but this is a bit more than that even, right. Here what you have here, the joint distribution factors into the product of the marginal distributions, right. Here actually you are seeing it is this, not at this line, but if you look at this line, what you see here is that this is a proper probability distribution, this is a proper probability distribution, and this is the joint probability distribution. This factors into product of its marginals. This is the nicest thing that you could have, right. This is also under this scenario, but this is sufficient for us to call this as a product form network. Okay. But this is what is happening here. So, this form of solution indicates that in steady state, each node behaves independently of the other, otherwise this would not have happened, right. One could expect that the say from node 1 when they come out, right, the average rate of output could equal lambda, but what we are seeing here is more than that, not just the mean rate of arrivals or the mean, but even the variance, in fact the whole distribution same. So, that is what the second stage behaves like a system with an input process that is Poisson with rate lambda, and that is it behaves as an MMN queue. independent of the behavior of the first stage. So, it is basically, this is what is important here, and this is it behaves in this way. Whether this can be proved, yes, if it can, this can be proved if we can characterize the output process of the first node. If we can somehow specify what is the nature of the output process of the first node, then possibly like we can explain this behavior. Okay. So, this output process basically what is the distribution of time between successive departure of the first node is the input process to the second node. That is what is in this situation it happens. Now, how do we characterize is what is the result which is known as Burke's theorem, who gave the result in 1956. And this determines the output process of the MMCQ. So, what we have considered is MM1, but in general it is MMCQ, and it can be shown that all the systems with the FCFS discipline, MMC is the only system with the stated property that the output process is really a Poisson output process is exactly same as the input process to such a system. That once we do that, then we have explained the reason why and how this is happening here, and how this is becoming in this form that you have here. Okay. So, that is what we will see, and with that result then we will generalize this 2 node to multiple nodes in this particular fashion before we go take it up to any other node. Okay. So, that we will see in the next lecture. Okay. Thank you. Bye.